First of all, we have to talk about the general issue. The general issue is about some tips. First of all is geometry of your design. You have to think or to know that the geometry of the design will be the common part of all the modules, either thermal, magnetic, electrostatic, or stress analysis. So when you design your plunger or your appliance, you have to think to add to have an exhaustive geometry as soon as possible. For instance, here I have some parts are not useful for the design, just as a stroke. Here, for instance, the stroke is not useful to check the insulation of our design, but it must be here to be common to every module. You must think about linearization. Linearization, if you can do it, you will gain a lot of time of simulation. Here, the linearization is important only if the plunger never touches or is never in contact with the body, or else you have some saturation. And if you have some saturation, you have to use a non-linear model. Also, don't forget that transient simulations are longer than the DC simulation, because a transient is several times the simulation, but at different steps of time. And if possible, just use circuits for your design. Here, the second circuit is very simple for a plunger, but when you deal with transformers, for instance, it's very useful to be sure that the accuracy of your model is reached. So, what about thermal simulation? So in a thermal simulation, you have two possibilities to introduce the power or the losses by Joule effect. Either you have another problem, you have calculated an electrical problem, or you can put directly the thermal power in your model. So what I've done here, I've introduced directly the power, the thermal power due to loss Joule effect in the model. It's quite easy to calculate it. I just simply use this formula. I mean, just to show you something before. The volume power for the heat source in QuickField is defined in watt per meter cube. per cube meter. So you have to calculate it before. So I use the formula this following. The volume of copper is the length of the wire times its surface. And also we know that the resistance of the bobbin, of the winding, is this resistivity times length divided by surface. In QuickField, we have the possibility to calculate the resistance easily. So I've calculated with QuickField that it's 0.6 ohm. From then, I can have the surface of the length of the wire. As I know the surface of the wire, I get the volume of copper. The power is given by this. We have our 10 volts, and we have our resistance. So the power is the square of the voltage divided by resistance. And at the end, we can easily have the power density that is due to Joule effect. This example was calculated for a pulse due to power. I mean, it's just like a short circuit or this kind of thing. So here, I've taken my power density time an impulse. I mean, here we have an impulse that will last 1 second, from 0 to 1 second. And we can see with the time what will happen. Now with QuickField it's easy to know what is average temperature in the winding. We have just to click here, find a contour, have to clean it before, integral calculator, average volume temperature, and I have to ask to calculate the time plot. You can see that my calculation is finished. So we have the increase of temperature. So during 1 second we have our over voltage or our power due to the Joule effect. And after 1 second it is stopped, and then the temperature is falling down. But we can see that we have attained a 50-degree difference with the start at the start.